All right, so you might have, we just had a little bit of a discussion about the mask, and Justine has very succinctly explained the, the nuances of choosing the mask. So all we do here is, in this particular step, I'm coming back to R, by the way. So in this particular step, we create a mask on this command here. Um, okay. So we're saying make mask. And what I'm saying by make mask is I'm telling the software to use all the traps from my data. And what is this all data dot large? We just created a make cap hist, or we made a capture history with that, with this, with the capture data and trap data. So this is that data that we created. So we have to create around these traps, we have to look for a buffer of 15 kilometers. And this is in this particular case, the one that I'm working on, we knew, or at least we had a rough idea about what the sigma was. I was using a sigma of 3, roughly around 100 square kilometer ranging of home range size, and with which we keep a sigma or a buffer of 15,000 meters, which is 15 kilometers, and we define it as a trap buffer. Please know that a buffer can be defined in many ways. You can have a shape file, you can have camera trap grids and create a buffer around them. If you have, like Justine showed that map of South Gobi, if you have a landscape where there are hard boundaries on all sides, then you can use a shape file as it is as a mask also. If you have a buffer like this, and you have certain, let's say you have a big lake in between, and the lake is impermeable, then you can simply remove that from the mask by using a shapefile as well. So all these flexibilities are available. You can use shapefiles, or you can take the data back to GIS tools and fix them. Right. So once I have all the 3 data types that I needed, I have all my trap data and capture data in this little variable here, this object here, which is called all data.large. I have my mask, which has been defined as Spiti mask large. Large here stands for the large trapping design, right? So that's why I've just used the word large. And that's all I need to know as far as data is concerned. Here I am defining density tilde 1, which basically means density is constant. Here I'm defining lambda tilde 1, which means lambda is constant. Here I'm saying sigma tilde 1, which is sigma is constant. And this important step here that you will see, this one, HHN, how is my detection function? You remember we were using a detection function. So far we've been talking about this half normal. There are many types of detection functions. There is an exponential detection function. There is a hazard rate half normal detection function where animal use of space is constant until a certain distance and then it suddenly dips. This is the normal half normal distribution, and so on. So HHN here stands for hazard half normal, if I remember it correctly. But basically, this is the standard that we are using right now. The moment I punch in this command and press Control Enter or click Run on my R console, it starts running an analysis. Now, look carefully here. I've just captured a screen grab here, and there are these 3 parameters. You recollect these are the 3 unknowns that we are looking for. So what the solver is doing right now is it is taking, it's running with all possible values of d, lambda 0, and sigma. Actually not the real values, but the coefficients. So it's taking a value which, say, let's say from -infinity to +infinity of all these 3, And it's basically putting these values in the solver and testing that what is the likelihood if that my coefficient of density is minus 8.5, my lambda zero's coefficient is minus 0.001, and my sigma coefficient is 7.88. What is the likelihood? So it basically estimates likelihood of each of these combination of three values given data. Sometimes there is a failure, so it just skips those steps, and it basically starts running this likelihood exercise for several iterations. What it ultimately does is uh, right. It runs it over all the way, and at some point it starts seeing that, okay, I'm close to the peak, and then it stops. At this point in the analysis, it really was able to say that there is no other value of the coefficient of density, lambda zero, and sigma for which there could be a higher likelihood. In other words, I mean, this is happening in the negative space, so it's actually an inverse mountain, not the way the mountain looks like, but the opposite of mountain. But at this particular value, for all the variables, you have found a minima. And look carefully, it took it 6.5 seconds to do this. We are using computers which are pretty fast, right? We have almost 2.63 gigahertz speed at which our computers work. With such speeds, it's still taking 6.5 seconds. You can imagine the number of iterations and calculations it's going through to come up with the most appropriate combination of these three variables. So once it has done this and there is no error and it's successful, then it just stops here. And what we then do is we check our output. How do we check our output? First, we go to checking coefficients. Now, coefficients are those values which are being for which maximum likelihood is being estimated. Now, why are we looking for coefficients and not actual values? I'll just try to explain in a couple of seconds. But basically, it's looking for the minimum value of these coefficients. Sorry, the values of these coefficients for which the likelihood is the highest. In this particular scenario, the log likelihood to be the lowest possible value mathematically. Now, these are the three coefficients that we come up with. Now, why are these not D as density? Density cannot be negative. Lambda 0 is fine, sigma is 7, it's all right. But what you need to look here is that we are not estimating these parameters in a linear scale. Now, I have a small example to try and explain that, which is here. Now, look at it this way. You have a variable x which is varying between 0 and 10. And then you have a variable y which is varying between -5 and +5, right? So you may have a linear scale from here to here. Now, you can create an equation of straight line, and then for any value of x, you can predict what would be the value of y. What if the value of x reduces to -1? Then it's going to say that your y will be somewhere minus something, right? Now, that's practically impossible. In other words, a density can never be negative. You cannot have -3 snow leopards in a study area. There can be a minimum of 0 and a maximum of whatever number of animals can live in that particular space. So you can never have 0 snow leopards in a certain area. You may have a certain number of snow leopards. And so is the case with lambda 0, which is the encounter rate. You can't have -5 encounters. You can either have no encounters, or you can have 20 encounters or 100 encounters or whatever at the activity center. So it's a very important point to remember here that our estimated parameters cannot take a negative value, which is why we estimate everything on the exponential scale. So the whole likelihood is estimated on the exponential scale, because for any value of x, the y will never be less than 0. And that's a fairly easy and a useful way to work around this particular scenario. You can have any value of minus 5,000, y will still be very, very close to 0. You can have a value of plus million, y will obviously be exponentially positive for that value. So technically speaking, this is the reason why we use it's done on an exponential scale, and the calculations are fairly simple. Once you have the coefficients, this is the coefficient that we have obtained the maximum likelihood for, right? These are the three coefficients. You simply do an exp on a calculator or Excel or even R. Just type exponential of minus 9.50937. It will quickly give you this value, which is the predicted value of density for my particular study. In this case, I got a certain kind of a detection function. The solver had no idea about the activity center, the encounter rate at the activity center, or the ranging parameters. It tested all possible values of the three unknowns, and then at one point it said, aha, this is the most likely value of sigma, lambda 0, and the density. And that's the value which it has provided us here. This can be read. Now, you have to remember that uh, spatial capture recapture estimates density in hectares. So this value is in hectares. If I translate it into per 100 square kilometer, not even 100 square kilometers, or not even per square kilometer, it comes out to be 0.74 snow leopards per kilometer square. That comes out to be my density of snow leopards. You can try this by simply doing an exponential of this beta. You can do it for lambda 0 as well as for sigma. And what sigma here says, the ranging parameters is nearly 3 kilometers. I know for this data, because it's a simulation data, we had kept sigma to be 3. It has estimated sigma to be 2.94, which is as close as I believe it can get, and it's a fairly good estimation. 2.8 is indicating the number of snow leopards that might be captured if by chance you had a camera trap right at the activity center. And that's 2.8, almost 3 snow leopards getting encountered if you had camera traps at the activity center. Right, so this is the first way estimator. So now, based on this this function, predict for my Spiti large.hhn, which is the SCCR fit model that I have run a couple of slides before. Over here, there we go. I use SCCR.fit, and the output was saved as Spiti large.hhn. The output here looks like a reasonable estimate of what we actually came up with. Now, on the next one, we need to know how many snow leopards are there in this entire landscape. All I do is I use the function region.n, where it simply, so basically now I know the density of snow leopards at each pixel, right? And based on that density, we simply calculate the overall abundance for the whole study area. And this region.n function helps us do that in a single step. You can estimate by just calling region.n for Spiti, I can get an abundance of snow leopards for this entire mask. If I wanted to know the abundance of a smaller area within the study area, I would have simply put a comma and given it a new name. I would have created a sub-mask, a smaller mask. I would have called it, let's say, protected area or whatever, and I would have estimated it for that particular region. So that's one way of simply estimating the abundance, because that's what most people want. People sometimes don't want density, they want to know how many snow leopards, then you can simply use the abundance within a smaller area of interest once you know this. So in our case, what it's providing us is these two estimators. They can at times be confusing, and they still confuse, at least us, they confuse a lot. But the difference you can consider as, one is the estimated abundance, the other one is realized abundance. Estimated abundance gives the estimate of snow leopard abundance um, purely based on the model parameters of lambda, sigma, and density. Realized abundance is estimated almost as a not a function, that's not the right word, but it basically considers, okay, you have photographed 20 snow leopards, so they cannot be less than 20, more than 20, and these are the 20 snow leopards. Where, how many more snow leopards you have in your population, and that usually is how realized abundance is calculated. And the differences between them sometimes are not very substantial. They're usually very close to each other. But if you look at this, typically these ones have much more precise values. So most occasions we report these as the abundance, if abundance is a parameter of interest to be showcased or to be reported. Now, so Justine just explained very nicely how do we, uh, how that, you start with the 4 sigma or a much bigger value, and then you really don't want to waste your time running an analysis for space which is outside your area of interest. Now, what you might truly be interested in is, and then also there is another challenge, that if I'm sampling in a small area and I'm predicting snow leopard density to be the same across, let's say, 5 times or 6 times or 7 times that region, I'm really making a huge leap of faith by saying snow leopard density is constant or whatever it's here. It's the same function, let's say 30 kilometers away as well. Sometimes that could lead to a gross overestimate, or it could lead to substantial errors in interpretation, which is why we would like to reduce the buffer as much as possible to a reasonable limit. But remember, reducing the buffer does not change your density estimates as long as you don't reduce it too much, which is when you end up with biases, right? So if you're reducing the buffer to a certain extent, density shouldn't change. And in this case, what we do is we provide it the same value that we estimated for our last run model. So we give it the value of lambda 0 from our previous model. We give it the value of sigma from the last predicted model. In other words, if you look at it here, I give it these values. From here, I'm picking, I mean, I was a bit lazy here, but I could have just picked up these values and typed them there. Instead, I've just referred to them so that when they change, they still remain the same. So I have used these two values there, and I'm just referring them as second row, second column, second row, second column, third row, and so on. So that's the only way, the difference in which how I'm referring to them here. But if you look at it carefully, you will see that, yeah, second row, second column, third row, second column. And this is how I provide my sigma and lambda 0. Here we are defining the error that we can live with. In other words, we are saying that we are okay to end up with a bias of 1 in 1,000 or 0.1% by not making the buffer big enough that it takes forever to analyze. And of course, there are other interpretation issues there, but to keep the buffer as small as possible, where the bias, positive bias in my estimate could be 0.1%. And I think that's a reasonably negligible fraction of snow leopards that might be able to walk even from further away from this predicted distance and get photographed on our traps. So when we use the initial lambda 0 and sigma data here, it comes up with a suggested buffer of 9,561 meters. I can keep it 9,561, or I can just round it off to 10,000 and run the model again. So this time what I have done is I have I have used this estimate here, and I have created a new mask where instead of 15-kilometer buffer as we did last time, this time we take a buffer of 10 kilometers, and I run the analysis. So over here you see the little animation. It's not very intuitive, but basically the mask is changing from a larger area to a smaller area. So you can see in one case over here, if you notice carefully here, you will see this is the first mask of 15 kilometers, and this is the reduced mask of 10 kilometers. This is the one that we are now using in our analysis. When I use this when I use this new mask, I've called it Spiti Mask Large 2, just for convenience sake, to be able to remember what it is called. I just gave it a name 2. And when I use this one, everything else is the same. All data large is the same. The models, everything is being assumed constant here. Hazard half normal is the same. When I run this model and I click on coefficients, I get these coefficients, and these are the predicted estimates that I get. When I compare these estimates with my earlier analysis, I was a bit surprised. Well, actually not really surprised, because you see the two estimates are almost the same. The errors and other parameters over here you will notice are incredibly close to each other. Now, this is because we were anyway using a much larger buffer to what is being suggested. So we are not really biasing our results any further. And what it also tells us that is that instead of 15 kilometers, if I bring it down to 10 kilometers, I'm not biasing my results. So it's a safe buffer for me to use, and I am fairly confident, based on our data, we can be fairly confident that a negligible fraction of snow leopards from outside this 10-kilometer buffer are coming in and getting photographed on our camera traps. So that's exactly what we have done right now. In fact, what it has benefited us is by increasing the speed of our analysis quite substantially. So when but then there is an interesting factor, and it's something that you will notice when I use the region.n, which is I estimate the abundance from this new mask. I end up with much fewer snow leopards. Now, how did that happen? Now, that's a bit of a problem, or maybe not. But can someone in the chat window tell me why has my abundance reduced so much? My density didn't change, my lambda didn't change, my sigma didn't change. What happened? Why has the abundance suddenly gone down? So just take 1 minute to quickly think through what may have happened here. Anybody?
Yeah, write in the chat, anyone, if you have thoughts.
Yeah.
Everyone was thinking, Gustav, they just weren't writing.
Oops. Okay, no, sorry, no comments so far. Can anybody tell us quickly why has the abundance gone down from 72 to 59 in this case? Even though my density is the same. Well, let me admit it here. It's a trick question. It's not a stat or math question. It's a trick question. Smaller area. There we go, Ranjana. That's exactly the answer. Yes. It's the same thing. We have a smaller mask, so there is a smaller area we're looking at. So obviously the number of animals at the same density. It's like, you know, I have a big plate and I have 20 beans on it. I have a small plate I cannot have 20 beans, they'll just spill over. So I will have 15 beans on the same plate. So it's just that I've reduced the area. So obviously some snow leopards which were expected to be in the population have gone out of my study area, and hence I have a smaller abundance in this case. Very good. Thank you very much, Ranjana. That's a good answer. Let's go to the next slide now. We'll just change gears a little bit here to move quickly, but please be warned that we'll be running out of time, so kindly bear with us. There's a lot of ground we have to cover today. This is a second scenario where we had sampled a small area with a small number of camera traps. We had 12 cameras, we had to sample it. Someone said, oh, I have 12 cameras, let me just put them and see what happens. As a matter of chance, this person ended up going to a certain area, and maybe someone told the person to go to this region, go here, because this is where people have been seeing a lot of snow leopard pug marks and scrape sites, or maybe the person has chosen it randomly. In both the cases, you will end up with different kinds of results. So one reason why you have to be extremely cautious and careful with very small sample areas. Now, in this case, what will really happen is you've ended up in an area, or I have deliberately ended up sampling in an area where we see a lot of animal activity. And you see, and this typically happens, right? If you go to parts of, let's say, Ladakh, people say, oh, go here, you have a lot of snow leopards. You go out, set up 15, 20 cameras right there, you'll get a lot of captures, but that does not tell us much about the whole Ladakh region. It can just tell us something about that small part, let's say Rumbak or Saspoche or wherever we're talking about. Now, when you set up the cameras, because it's a very good site with a lot of snow leopard activity, here, as you will notice, we have ended up with a lot of snow leopard photos. In fact, snow leopard photos on all cameras. I think one camera hasn't recorded anything, but apart from that one camera, we have recorded snow leopards everywhere. Look here, what you see is each snow leopard, each camera has had some encounters. At least on this screen, you don't see any encounters for C1, but apart from that, each other camera has had encounters that you can directly relate. C2 has captured snow leopard number 16. C2 has also captured snow leopard number 16. Now, these are all captures of 16 here. There is another snow leopard number 7, which has been captured on C8, but C8 has also captured 16 quite a few times. So essentially, this is the kind of data you end up with. You will notice most camera traps here have encountered snow leopards, and that's quite possible in a real life scenario if you have chosen a very high activity area where people report, yeah, we see scrapes, we see snow leopards, or we see snow leopard and snow leopard activity around this region. So that's what you might end up with when you run this analysis. Again, I'm skipping those steps that we've done earlier, but if you run the analysis, you come up with a certain coefficient, and when you predict, you suddenly see that your density seems to have increased almost 30 to 40%. There are differences in lambda 0 and sigma as well. Let's do a comparison, one-on-one comparison. When you do that, here is the current output, and here is the output from the large sampling design. You see from 0.7 animals per 100 square kilometers to almost 1.1 animal per 100 square kilometer. The density seems to have been taken a jump. Now, it's not wrong because we are still getting a detection function. The only thing here is that this is right or accurate for a very small area of our interest. That little mask that we have created, that little patch we have estimated, this might be true only for that, or maybe not even that much, because there could be variation right outside our camera trap frame, which we may not be capturing in this particular design. So, sorry. Now we move on to the third scenario, which was an intermediary camera trapping frame. This is typically how we should plan our studies: have a sufficient density of camera traps, have a good enough density of your camera traps so that you encounter many individuals, many times on many cameras. Please understand, several snow leopards, several cameras, several encounters. That's what we look for. Did I say it right? Several snow leopards on several traps on several occasions. Yeah, three of those severals you have to look for. But if you look for a design like this, then you might end up with a data set which will look something like this. For each snow leopard has been captured on a certain camera, and that is reported here. Snow leopard number 5 has been captured on camera 24. Snow leopard number 10 has been captured on C45, 52, 44, 53, again on 52, again on 52, again on 43, 44, again on 52, and 44, and so on. So this one snow leopard number 10 has got captured several times on a few cameras. But the good news here is that it has gotten captured on multiple cameras, which is exactly what we want for our data to become useful to estimate those unknowns that we have. And when you look at the outputs, you see we have this particular camera C3 having captured snow leopard number 1 that you can see in this particular frame. Sorry, snow leopard number 7 on this particular frame, and then so on. You will have capture histories and associated trap data for all the other animals. When I run the analysis, again, SCCR.fit with this new data, with the new mask, with the new trap data and new cap data, my coefficients are, these are the coefficients for which the likelihood got maximized. When I predict it, I get an estimate which is much, much closer to reality. Again, I know it because it's a simulation and we had defined a few parameters right in the beginning, but you see we come up with a fairly reasonable estimate here of 0.8 animals per 100 square kilometers, with a lambda which is slightly overestimated in this case, but a sigma which is actually lambda I have no idea. Sorry, forget about ignore what I said. For a lambda 0, which is indicating there could be 3.5, 3.6 animals captured if your traps are at activity center, and then sigma of 2.9 kilometers, which is roughly around 3 kilometers as we knew in this particular case. So when you, so this is the third design. And if you look at the comparisons, you see there are minor differences between the three, but still none of them is glaringly wrong. And this is one of the strengths of spatial capture recapture. You have to do it terribly, terribly, terribly wrong for it to fail completely. It's an incredibly robust analytical tool, and the kind of estimates we've tried with various simulations, it takes a lot of effort to do something wrong. But please understand that minor differences in the design can lead to substantial changes or differences in the final estimates. Lastly, this was a cluster design that we had set up, and in this design you can see we have we had these 4 clusters. I added a few additional cameras here just to be able to give it some more data to play around with, mainly because I wanted the numbers to be similar, number of cameras to be similar, 56 in the first 2 cases and 56 here as well. So when I use this, when I use this data, again, this is how I will enter my capture data. I'm sorry for repeating a few steps, but please try to understand these are exactly the kind of the way how we will enter the data sets. The trap IDs and the capture IDs would come in here. And when I enter this data to my analysis, I will, let's see. Now, when you see in this case, for now, we're just seeing one of the many examples of captures, but we know Snow Leopard ID 7 has been captured on camera number 8, which is at this particular location, and so on for all the other cameras. So we can basically see all the other cameras here. And when I analyze the data, I run the analysis, I come up with an output of, I have my coefficients here, and you get the following predicted density estimates and the estimates of encounter rate at activity center and the ranging parameter. The outputs here, compare them with the other ones, you will notice that there are, again, it's different. It's slightly, this one in this particular case got slightly overestimated, and it could have been a chance because it was still subsampling a much smaller area. Now, 2 points, I mean, one word of caution that these simulations are just one simulation each, and there is a fair chance of it being right or wrong. Any simulation should be tried hundreds of times. So while these are just for a representation's sake, when we run these several times, and I ran some of these about 100 times each, you start seeing that over a longer number of simulations at various possible combinations, the two models, the two designs which come up to become the most robust and the most have the least bias overall end up being the one which has the intermediary trap distance and the one which is this cluster design. These two typically are closer to reality as compared to the other ones. This one, in our case, it wasn't a very bad design because the inter-trap distance was still not too bad. It was still such that many snow leopards were able to get photographed on multiple cameras. Hence, this did not fare very badly. This fared to some extent, this fared badly. Just ended up overestimating it, but it could have been a matter of chance that we ended up sampling in a high density area, but because someone asked us to do so. We could have ended up in another area with a completely different and an inversely opposite result. So with that, we stop the second part of this this conversation. If you have,
Can I
yes.
just quickly add, I mean, these are great examples that you can actually test using the SCR toolkit, the Shiny app that we shared with you by email last week.
Yes.
And you can play around. You can do a grid cluster design versus a systematic versus a random design with your camera traps. If you can get an estimate for sigma, lambda, and potential density for your population, and then you can simulate this online. So Helena was asking questions related to understanding how it would differ. Well, you can actually test that using that
Absolutely.
app online. So that's a way to test these models. Yeah.
Exactly, and thanks, Justine, for bringing that up. As Justine mentioned, we have a pretty a powerful little app which takes the same sort of principles to physically test the most appropriate designs and come up with the most approximately optimal design for camera trapping. And that's something that Justine just explained. I think that's a really powerful little tool we have to help design your sampling. All you need to do is tell how many cameras you have, what is your area of interest, and of course some basic expected guessed parameters, and it'll come up with a few optimal designs that you can use in a particular study area. Okay, so just quickly at this point in time, I was just wondering if you should do this or try and finish it first. But if you can, if you guys can type in the chat window, what could be the potential sources of biases and errors in a sampling design? It's just a recap. So if you could think through quickly, and then next couple of minutes, that'll be really helpful for us to move on to the next segment, which will be kind of a little bit of an intense roller coaster ride into non-uniform parameters. Anybody would like to point at what could, okay, there we go. Thank you. Okay, that can cause biases. Very good, Ranjana, thank you. Others, please. Or Ranjana yourself as well, please send in more possible sources of biases. Come on. Last turn. Yeah. So, to be honest, if you have a very large study area, you won't be biasing your sampling. If you have enough cameras, let's say you have 500 cameras, you can go out and sample 5,000, 6,000, 10,000, 15,000 square kilometer area. That's fine. The biases come in when you are sampling a, a certain type of a habitat and using it to explain the density or other parameters in another type of habitat. But very honestly, if you have a very big area and you have enough resources, like Madhu Chetri's work, 15,000 square kilometers, he could do it not because he was using camera traps, because he was using genetic sampling transects. He could cover the entire area fairly well. So that's the key point we need to look at or consider here, is that larger areas, if you have sampled them well enough and there's no bias in your sampling per se, that you're not going, oh, I can't go to these difficult areas, I won't sample there, I will only sample in the easy to go areas, then larger areas don't create an error or bias. They only make it more difficult. Biases happen when you sample too small an area, or you end up sampling in a disbalanced way. Arslan says large areas, less samples. Okay. Good. Anybody else? Justine?
What about misidentification, like we talked last time? That will really bias. Small buffer, if we assume just, for example, our camera track area.
Okay, so don't worry. We've covered a lot of ground, and I totally understand if it's been a little bit of a roller coaster ride. Not including mask. You can't run SECR without mask. Ranjana, I'm sorry, I think you want to say something else. If you could just mention
Maybe
that.
not buffer. Maybe she means no buffer, like just.
Yeah, so we can say small or no buffer.
Oh, and yeah, including unsuitable areas. Very, very true, Ranjana.
Okay. Okay. Variation in number of individuals. I'm sorry, I don't. Justine, can you help understand? Variation in number of individuals and their detection histories, which may be the same as misidentification.
Maybe if you just have certain individuals captured on one camera. So if you have half of your population just captured on one camera, so you can't estimate, for example, sigma for your individuals. So single captures, maybe single.
Is that what you mean to say, Helena? Because in real life, there will be a huge variation in the number of times you will get snow leopards captured. Some snow leopards might be captured once or twice. Others might get captured 30, 40, 50 times. So that's a difference. I mean, that's one scenario which is quite likely going to happen. But I think, yes, there is, if you are sampling in a way that you're not giving, yeah, if you're, again, I think it's more like a bias in your sampling. Okay, so I'll stop here, and insufficient capture. Yes, if the car insufficient capture can definitely lead to a bias. But so what do you mean insufficient capture? Not getting enough snow leopards on camera traps? Ah, you're saying not getting enough captures should not be a bias. Okay, we'll come back to that question, Iftikhar, if you can hold on to it, uh, because we are already late and we have another at least 30 minutes to go
Yeah.
in the talks that we have lined up. So we'll come back to that, Iftikhar, but please keep that question with you because yours and one more question by Helena are the ones we have to address, and we'll come back to those. Okay, let me quickly go to the other